Hi guys, this is the second part of 12B, and I got to part 6 here in the investigation on the previous video, and I stopped and I just thought about the language, and it just made me pause a bit because I wasn't quite sure with the language. It says, how do you find the component of a vector A acting parallel to a vector B? Well, I was thinking, I think what they mean is that A and B are parallel here. And how much of A is acting in the direction of B? Well, all of it. I think that's what they're trying to get at. I was just wondering, because it said how do you find the component of a vector A which is acting parallel to a vector B? Well, if A is like this, we're saying this is A and this is B. Just drawing them up actually. Okay, and you're saying, well, how much of that is acting parallel to this? Well, that's just the technique which we did. This amount which is acting parallel to B. Is this amount here from here to here. But I don't think that's what they mean. They mean that A and B are parallel vectors. So how much of A is acting parallel to B? Well, all of it, if they are parallel vectors. And I think what they mean is by the second one. So I think the language is slightly ambiguous. It says if the two vectors are perpendicular, so there's A and there's B, how much of A is acting in the direction of B if A and B are perpendicular? That's what the question should say. And so none of it is acting in the direction of B. So it's all acting at 90 degrees to B. So none of it is acting either up this line or down this line. It is acting perpendicular to B. Okay. So, right. So let's have a look at the next little bit. Now, there's a bit more in this formula here, actually. If we just take this, because it says just what we've gone through. It says given two vectors A and B are A and B, the component of A in the direction of B is given by this thing here. So the dot product divided by the length of B. But then it says the component of A perpendicular to B within the plane defined by the two vectors is the magnitude of the cross product. Okay, so we're going to have to unpick that one a little bit because they don't tell us about that. So let's come up with two vectors again. Let's say here, let's go A and let's go B. We're talking about we're talking here about the component of A perpendicular to B within the plane defined by the two vectors is this. So it's saying how much of A is acting perpendicular to B. So what they're trying to get you to do there is find this bit here. Now, so for that, we're not going to use cosine, we're going to use sine. There's your theta. And if we want to use, if we want to find the opposite in this triangle, we know SOH gives us that the opposite is sine of theta times by the length of A. So that would be equal to, now they're saying that's equal to this. Let's just check that for a second. Where's that coming from? So kind of doing this back to front a bit. It's saying that that's the same as this thing here. So instead of doing the magnitude of A cos theta, which is where this came from, we're doing the magnitude of A sine theta. And then this. Where's that coming from? Well, that is your cross product, remember. The cross product is here, it's saying A, B, sine theta. So there's your cross product. The magnitude of the cross product is equal to the magnitude of A times by the magnitude of B times by sine of theta. That's what we know from before, from chapter 3, but that's rearranged to give you this thing here. And this thing is telling us how much of A is acting perpendicular to B. In other words, what's the size of this green vector here? How much of it is going up in this direction? You can split it into this one and this one. Okay, so this blue vector I'm just noting here is the same as the green one. That's how much of A is acting perpendicular to B. This blue vector, which I'm doing the second one there, is how much of A is acting in the direction of B, or parallel to B. Okay, hopefully that is clear, but they don't actually give you a proof of this one, so hopefully that is useful. Okay, let's look at the question on here. So example 2. So pick this. So it says a sailboat is traveling on a bearing of 45 degrees. So remember bearings. Oh, we've gone blue there. So 45 degrees from north. He's talking about the boat going up in this direction here. So that's a bearing of 045 degrees. That's 45 degrees after north. So that means that this angle here is going to be 45 degrees. Okay. So then it says the wind is blowing with a velocity of 40 kilometers an hour from a direction of 200 degrees. So 200 degrees is going to be just past 180. It's going to be like this. So that's blowing towards 200 degrees, but they say from 200 degrees, and they're really particular about from here. Just to think, if this is a sailboat and the wind is coming from almost in front of it, it's going to have a really hard time of getting forwards. It must be going in the other direction. So it's going, that's 100 degrees, that's 20 degrees there. Then, so that's 20 degrees from south, but 200 degrees from north, clockwise from north. So that's 20 degrees there. There's 70 degrees there. Okay, so that's where it's coming from. It's coming from 40 kilometers an hour. Now we can represent that by a vector of length 40, or you can scale that up or down. It's going to have a length of 40. So this one here should have a length of 40, and that's the direction it should be going in. Write down the velocity of the wind as a column vector. Well, what we need to do is split this one into its two components. It's a bit messy, that diagram. Draw that out again. You need to split it into its two components. So there's 70 degrees. It's got a length of 40. 40 there. Okay, so we need to split it into this horizontal component. Let's change the color. Let's go magenta, and into this vertical component as well. So for the horizontal component, we're going to have 40 cos of 70 degrees. Now it's useful to be able to get that really quickly, and I always think if you're going through an angle, that it's always cos of that thing. So the other one, so in vertically, you're going to have 40 cos of 20 degrees. Now that's the same as saying 40 sine 70 degrees as well. You can verify that by either using this triangle with sine, or by using this triangle with cosine. Okay, so that's what I've used. I've tried to use the magenta triangle there. So right angle triangle, we're looking for the adjacent, and so the angle here is 20 degrees. Okay, so let's take that back a little. So I would leave it in terms of cosine, to be honest, if I can. Keeps it all consistent. So that's going to be our velocity vector. So let's just note that as v. If you want, you can put on your units of meters per second. Okay, so that's part A. Part B, find the component of the velocity of the wind in the same direction as the path of the boat. Okay, so the boat is going along the path. So it's a bit like the formula from before. So the boat is going along the path of 1, 1. I don't know how fast it's going, but it's going at 45 degrees. Okay, so 45 degrees means actually 1 up and 1 across, or it might be 10 up and 10 across. We don't know how fast it's going. We don't have the velocity vector for the boat, but we do have the direction vector for the boat. So the direction vector is 1, 1, and the length of B is equal to the square root of 1, just 5 factors of that basically. So square root of 2. And that's just the direction of B. But now remember the formula which we had before. We had A dot B divided by the magnitude of B is what we need to work out. Now A in this case is V. So I'm going to do that. So V dot B is going to equal to this times by 1 plus this times by 1. That's what we do. So we're going to say That's 40 cos 70 degrees and plus 40 cos 20 degrees. And then to find the component which is acting in the direction of the boat, we'll need to divide by the length of that boat vector which we chose. So we'll need to divide by the square root of 2 there. So divided by this will give us the amount of v which is acting in the direction of b. So we'll put divided by square root of 2 there. Now when you've done that, you'll have your answer. That's how much of it is acting in that direction. That's the velocity of the wind which is acting in the direction of the boat. Okay, let's just check that in the answers. And there we go. You can see they've actually worked it out already. Okay, so I left my vector like this. They've worked it out, and perhaps that's a good idea to do for in an exam situation as well. You have both the exact answer and you also have the approximated answer there as well. In terms of the final answers, I would use the full answers there, not the rounded off truncated answers here and here. I would use the full answers saved on my calculator. By the way, they've used sine of 70. I used cos of 20. It's the same thing. Okay, guys. Well, I think that's it. You've got 12B to get on with after that. So thank you very much for listening. And I'm about to do the video for 12.